Alright, kiddos, welcome back. And we're going to continue our discussion of stoichiometry. This time we're going to include a concept called limiting reagent. So I thought I would start with a pretty simple example, one that I think we can all understand, and then we'll apply it to a chemical example. So let's say you want to make a very, very simple toolbox. And in that toolbox you have a set of pliers, 2 screwdrivers, and a hammer. Now, you have available to you to make these toolboxes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 screwdrivers. And you have 1, 2, 3, 4, 5 pliers. And you have 1, 2, 3, 4 hammers. Okay? Now remember, each set of tools in your toolbox requires 1 set of pliers, 2 screwdrivers, and a hammer. How many sets of tools can you make? Well, let's see. Since we have 10 screwdrivers, we can put 2 in this one, 2 in this one, 2 in this one. That's 8, right? All right. That means we're going to have 2 left over. For pliers, we can put 1 here, 1 here, 1 here. That's 4. So we'd have 1 plier left over, and we can put 4 hammers in here. 1 here, 1 here, 1 here, 1 here. And you'll see we have no hammers left over. So how come we couldn't make another set of tools? How come we were limited to just making 4 sets of tools instead of 5? Yeah, it's because we didn't have enough hammers. The hammers limited the number of toolkits we could make. Now we end up having some extra tools, right? We have an extra set of pliers and 2 extra screwdrivers. Boy, if we only had 1 more hammer, we can complete another tool set. Nevertheless, we don't. So we can't have a 5th set. The hammers limited us to the number of tool sets that we could create. So we were limited to 4 tool sets because of our hammers. Our hammers were our limiting reagent, so to speak. So the same thing happens in chemistry. We might have a chemical reaction where we need 2 reactants. And maybe one of those reactants we have in abundance. And the other reactant might limit us to the amount of product that we can create. That's the concept of limiting reagent. Sometimes it's called limiting reactant. So let me give you a chemical example now. Let's say that a student has 0.75 moles of aluminum, and she adds it to a beaker with 0.8 moles of hydrochloric acid. How many moles of aluminum chloride will be produced? Well, you'll notice that we have 2 reactants or 2 reagents here, 0.75 moles of aluminum and 0.8 moles of hydrochloric acid. One of those will limit the amount of aluminum chloride or product that I can produce. So first let's write the reaction, okay? We have aluminum wire, so that's just Al, and hydrochloric acid, HCl. I'm not going to put the AQ after it right now, just to keep it simple. You should identify this, I hope quickly, as a single replacement reaction. So hydrogen gas will be produced, and aluminum chloride will be my other product. Let's go ahead and balance this because we're still doing stoichiometry, so we have to start with a balanced equation. So to balance that, let me put a 3 in front of H2 and a 6 here in front of HCl. See, that gives me 6 H's on both sides. I need to put a 2 in front of AlCl3. That'll give me 6 chlorines and a 2 in front of aluminum. So I think that balances my equation. Now, we have 0.75 moles of aluminum, and I have 0.8 moles of HCl. Which one will produce the least amount of toolkits? Which one will produce the least amount of product? Aluminum chloride. So let's do the problem twice. Once for the aluminum and once for the hydrochloric acid. So we'll go from moles of aluminum to moles of my product, AlCl3, and it looks like that ratio is 2 aluminums to 2 aluminum chlorides, just using the coefficients once again from my balanced equation. So this will tell us how many moles of aluminum chloride I can make with that reagent. Now let's do the same thing for hydrochloric acid. Let's hop out of moles of HCl and get into moles of product I can make again, AlCl3. The mole ratio this time is 6 HCl's to 2 aluminum chlorides. And this will give us also moles of aluminum chloride. Now the one that can produce the least amount of product will be my limiting reagent. So let's do the problem twice. The first one we can do the math pretty easily in our head. 0.75 times 2 divided by 2 is 0.75 moles of aluminum chloride. So that much aluminum can produce 0.75 moles of aluminum chloride in this particular example. And let's do the same thing for my HCl. I have 0.8 moles of HCl. I'm going to multiply that by 2 and divide that by 6, and that equals, boy, we're only allowed one significant figure here, so 0.27 rounds off to 0.3 moles of aluminum chloride can be made with that reagent. So what is my limiting reagent? Well, it's the one that can produce the least amount of product. So my HCl is my limiting reagent, and I can make 0.3 moles of aluminum chloride. That means I'll have some excess reagent, which will of course be my aluminum. Okay, does that sort of kind of make sense? All right, let's try another one. Okay, so one of the few xenon compounds that form is cesium xenon heptafluoride. So this compound right there. How many moles of cesium xenon heptafluoride can be produced from 12.5 moles of cesium and 10 moles of xenon hexafluoride? So why don't you take a minute and see if you can do this problem, then come back and see how you did. See you in a second. All right, welcome back. Now first of all, did you remember to balance the equation? We have to always start with a balanced equation. So let's take a look. We have 1 cesium on both sides. We have a fluorine here and 6 fluorines there for a total of 7. So that balances. And 1 xenon on both sides. Well, hey, that equation balances quite nicely. It's a 1 to 1 to 1 mole ratio. So let's go ahead and start our problem. We have to do it twice, one for each reactant. So 12.5 moles of cesium fluoride, and then we have 10 moles of xenon hexafluoride. So let's find out how much product I can make. We'll work the problem twice. We'll hop out of moles of cesium fluoride and get into moles of cesium xenon heptafluoride. It's a nice pretty 1-to-1 ratio. So this reagent will allow me to make 12.5 moles of my product. And I think you guys are already working ahead of me and you have the answer, don't you? This was sort of an easy one. Here we'll get out of moles of xenon hexafluoride, and we'll get into moles of cesium xenon heptafluoride, and that's also a 1-to-1 ratio. And boy, there we go. Looks like this one allows me to make 10 moles of cesium xenon heptafluoride. So it looks like my xenon hexafluoride is my limiting reagent, and I'll be able to make 10 moles of product, cesium xenon heptafluoride. Okay? All right, let's try another one. Example 8. The reaction between solid sodium, so we're reacting sodium, and iron 3 oxide is one in a series of reactions that inflates an automobile airbag. So we have sodium and iron 3 oxide. It produces 3 sodium oxides and 2 irons. So we have 100 grams of sodium and 100 grams of iron 3 oxide are used. Determine the following. I want the limiting reactant, the reactant that I'm going to have extra of, we call that the reactant in excess, and the amount of solid iron that I can produce. So the equation's already balanced for us. That was nice, isn't it? It's a 6 to 1 to 3 to 2 ratio. So we have to do the problem twice. So we have 100 grams of sodium, and we have 100 grams of iron 3 oxide. And we want to find out how much iron I can produce. So for the first one, let's hop out of grams of sodium and into moles of sodium. Let's find out what a mole of sodium weighs. We'll look at our periodic table. There it is for us, 22.99 grams. And then we want to go from moles of sodium to moles of the product we're after, and we're after iron this time. That's what I asked for in the question. And the mole ratio is 6 sodiums to 2 irons. So 6 sodiums to 2 irons. And I want to find the mass, so let's convert that to grams. So we'll go from moles of iron to grams of iron. So let's find out what a mole of iron weighs. Looks like it's 55.85 grams. So this will give us grams of iron from that particular reactant. So let's go ahead and do that math right now. So we have 100.0 divided by 22.99 times 2 divided by 6 times 55.85. And it looks like I'm allowed 4 significant figures here. So 80.98 grams. 80.98 grams of iron can be produced with 100 grams of sodium. Now, I gave 100 grams of iron 3 oxide, so we need to do the problem twice, remember, to find out which one is my limiting reagent. So we're going to hop out of grams of Fe2O3, and we're going to get into moles of Fe2O3. So what does 1 mole of Fe2O3 weigh? Well, let's see if we can do that off to the side here. We have Fe, and there are 2 of those, and they weigh 55.85 grams apiece. And we have oxygen, 3 of those, and if you remember, oxygen is 16.00 grams each. So 55.85 times 2 gives me 111.70 grams for my iron, and 3 times 16.00 is 48.00 grams for my oxygen. So let's see what the mass of iron 3 oxide is. We get, looks like it's 159, if I did my math right, 159.70 grams per mole. Alrighty? So we want to get out of moles of Fe2O3 and into moles of the product I'm after, which is iron. And that looks like it's a 1 to 2 ratio. So 1 Fe2O3 gives me 2 irons. And then we're going to go from moles of iron to grams of iron again. And 1 mole of iron is 55.85 grams. So let's see how much iron I can make with 100 grams of iron 3 oxide. So let's do the math. 100 divided by 159.70 times 2 times 55.85, and that looks like it's 69.94 grams of iron will be produced. So I think I know what my limiting reactant is. It looks like my limiting reactant is the one that produces the least amount of product. So my iron 3 oxide is my limiting reactant. That's my answer to letter A. That must mean my sodium is my excess reactant. And the amount of product I can make is the smaller amount of the 2, and that would be 69.94 grams of iron. Okay? All right. Let's do one more just for fun. I hope you're having fun. Take a minute and do example 9 all by your lonesomes. It looks like you're going to have to write the balanced equation for this one. And see how you do by coming back to the video and seeing me do it. Alrighty? We'll see you in a few minutes. Alright, welcome back. Let's see, we have lithium reacts spontaneously with bromine to produce lithium bromide. So you have to write the balanced equation, and I'm giving you 25 grams of each reactant. And I want to know, once again, the limiting reactant and the mass of product I can make here. So let's start by writing the reaction. Lithium is Li. Bromine, I hope you remembered, that is a Brinkelhoff element. It's diatomic, so it's Br2, not Br. And lithium bromide, let's see. Lithium's in group 1, it's +1. Bromine is in group 17, it's -1. So lithium bromide is LiBr. Well, let's balance that quickly. We'll put a 2 in front of lithium bromide and a 2 in front of lithium, and we're off and running. So we have 25 grams of lithium, and we have 25 grams of bromine. And we want to find out how much product we can make, so we have two reactants here, so we have to find out which one's going to limit the amount of bromine I can make. So let's hop out of grams of lithium and get into moles of lithium first. 1 mole of lithium is, let's see, can't read it because I've written over it. All right, 1 mole of lithium is 6.94 grams. And then we'll go from moles of lithium to moles of the product I'm after. Well, there's only one product, lithium bromide. So it's a 2-to-1 ratio. 2 to 2 ratio. Alrighty, and then I want to find the mass produced. So we have to go from moles of lithium bromide to grams of lithium bromide. So let's see what lithium bromide is going to weigh. So we have LiBr. So we know that Li weighs 6.94 grams, and Br is 79.90 grams. And so that would be 86.84 grams of lithium bromide per mole. So 86.84 grams per mole. So this will give us the amount of lithium bromide I can make with that reactant. So let's do the math now. 25 divided by 6.94. We can times it by 2 and divide by 2. That's fine. And then we'll multiply that by 86.84. And to 3 significant figures, it looks like I end up with 313 grams of lithium bromide that can be produced. Alrighty, so let's do the same with my bromine. We're going to go from grams of Br2 to moles of Br2. And 1 mole of Br2 would be the mass of 2 Brs. So remember, Br we just looked up a minute ago, 79.90. And we have 2 of those, so that's 159.80 grams per mole. Then we'll go from moles of Br2 to moles of my product, LiBr, and it's a 1 to 2 ratio. And then we'll go from moles of LiBr to grams of LiBr. And remember, 1 mole we just found out earlier is 86.84 grams. So let's do the math on this one. 25 divided by 159.80 times 2 times 86.84. That gives me 27.2 grams of lithium bromide. So it looks like my limiting reactant was my bromine. That's my answer to A, because it allows me to make the least amount of product, the 27.2 grams of lithium bromide. Alrighty? Alright, you should be pretty good now at stoichiometry problems, and you should have a good understanding of what limiting reactants are. So I'll practice these in class soon. Bye-bye.